The Reinforcement of Slab 4B. A novel by Gerald P. Hutchinson, B.Eng, Civil, Mice. Every slab tells a story. Most of them are load calculations. Preface. This book was not written quickly. It was written carefully, methodically, and in strict accordance with B.Eng 1992-1-1:2004, Eurocode 2, Design of Concrete Structures. The author wishes to make this clear from the outset, because a reader who opens these pages expecting drama, passion, or indeed any form of narrative tension will be well advised to manage their expectations accordingly. What follows is the true account, as true as memory and sight records allow, of the reinforcement of a concrete slab at the Haverstock Industrial Estate, Unit 4, Building B, Wiltshire, in the autumn of a year that was, in most respects, unremarkable. The slab in question was a 200 mm flat slab, ground-bearing, with a design-imposed load of 10 knots per square meter. It was not a bridge. It was not a dam. It was not, by any reasonable measure, interesting. And yet, the author spent 11 weeks on that site. He measured, he calculated, he marked out bar positions with a chalk line and a patience that surprised even himself. He watched concrete being poured on a gray Thursday morning. He watched it cure. He watched it do, essentially, nothing for several weeks thereafter, as concrete does when left to its own devices. It is that experience, the unhurried, methodical, profoundly uneventful experience of structural reinforcement, that this book attempts to capture. Whether it succeeds is a matter for the reader to decide, ideally while seated in a comfortable chair with no pressing appointments. The author thanks his wife, Margaret, for her patience. He thanks his colleague Derek Faulkner for reviewing the bar schedule in Chapter 7. He thanks the driver of the ready-mix lorry, whose name he never learned, but whose consistent arrival within a 15-minute window of the agreed delivery time he found genuinely admirable. Chapter 1 begins on the following page. Chapter 1, The Brief. It was a Monday. Gerald arrived at the offices of Perimeter Structural Consultants at 8:47, 13 minutes before his contractual start time of 9 o'clock. He did this every day. It was not a matter of enthusiasm so much as geography. The bus from Trowbridge arrived at 8:42, and the walk from the stop to the office took approximately 5 minutes, depending on whether the Pelican crossing on Ashford Road was in his favor. On this particular Monday, it was. He hung his coat on the hook behind his door. The second hook from the left, which was his hook, had always been his hook, and would, he hoped, continue to be his hook for the foreseeable future, and switched on his computer. While it loaded, he made a cup of instant coffee. He used 1.5 teaspoons of coffee granules, because 1 teaspoon produced a drink that tasted of colored water, and 2 teaspoons produced a drink that was, in his opinion, unnecessarily aggressive. 1.5 was a correct amount. His project manager, a woman named Sandra Okafor, appeared in his doorway at 9:15. "Gerald," she said, "we have a slab." Gerald looked up from his screen, where he had been reviewing the pile cap calculations for a scheme in Chippenham that had been sitting in his queue for 3 weeks and was becoming, in a quiet, administrative way, mildly urgent. "What kind of slab?" he asked. "Ground-bearing. Haverstock Industrial Estate. Unit 4, Building B. They want 200 mil, imposed load of 10 kilonewtons per square meter. Modest reinforcement. The contractor is Benfield Civil Engineering, which you'll know from the Melksham job last year." Gerald nodded slowly. He did know Benfield. They were a reasonable firm. Their site manager, a man named Roy Calder, was the sort of person who wore steel-toe-capped boots not because site regulations required them, but because he had worn steel-toe-capped boots for 30 years and saw no reason to stop. This was, in Gerald's experience, a reliable indicator of professional competence. "When do they want to pour?" Gerald asked. "They are hoping for the second Thursday of next month, which gives us," Sandra paused to consult her phone, "about 6 weeks for the design and bar schedule." 6 weeks, Gerald repeated. 6 weeks, Sandra confirmed. They regarded each other for a moment with the comfortable mutual understanding of two people who had worked together for 9 years and who both knew that 6 weeks was a perfectly reasonable amount of time to design a straightforward ground-bearing slab. "I'll get started," said Gerald. Sandra nodded and left. Gerald returned to his screen, opened a new project folder, and typed its name, Haverstock B. He stayed at this for a moment, considering whether the abbreviated name was sufficiently unambiguous, decided that it was, and began to gather the relevant standards. Outside, it was overcast. A pigeon sat on the window ledge for approximately 4 minutes, then left. The brief document. The formal project brief arrived from the client, Haverstock Properties Limited, on the Wednesday of that week, attached to an email from their project coordinator, a man named Philip Moss, who always sees at least 4 people on every email regardless of its relevance to them. The brief was 6 pages long. Gerald read all 6 pages carefully, made notes in his site notebook, black, A5, hardback, Sylvine brand, purchased in a pack of 6 from an office supply website, and then read the brief again. The key parameters were as follows. The slab was to serve as the floor of a warehouse unit, approximately 42 meters by 31 meters in plan. The ground conditions were, according to the geotechnical report, itself an admirably thorough document running to 4 to 7 pages, which Gerald had received as a PDF and printed, because he found it easier to annotate paper than screens, described as medium-dense sand with occasional gravel lenses, underlain by chalk bedrock at approximately 3.5 meters depth. The subgrade modulus had been estimated at 30 millinewtons per cubic meter. The imposed loading of 10 knots per square meter had been specified by the client on the basis of a future tenant who intended to operate a light manufacturing facility. The term light manufacturing covered, in Gerald's experience, an enormous range of activities, some of which were quite heavy, and he made a note to confirm with Philip Moss that the loading assumption was indeed appropriate, and that light did not mean, for example, that someone was planning to park a series of CNC machine tools or pallet racking loaded with dense metal components on the slab, which was a thing that had happened before on a job in Devizes and which had caused what could only be described as difficulties. He composed an email to Philip Moss. The email was 3 short paragraphs long, asked 2 specific questions, and contained no extraneous content. He proofread it once, then sent it. Philip Moss replied the following morning, CCing 6 people. The imposed load was confirmed at 10 knots per square meter with no concentrated point loads anticipated. Gerald updated his notes accordingly. Chapter 2, Ground Conditions and Subbase. The geotechnical report for the Haverstock site had been prepared by a firm called Groundshaw Technical Partners, and it was, as Gerald had noted, a thorough piece of work. He read it for the 3rd time on the Friday afternoon of his first week on the project, this time with the specific intention of extracting the parameters he would need for his slab design. Soil investigation had been carried out using a combination of trial pits, 6 in total, distributed across the site in what the report described as a grid pattern that was, in truth, a mild approximation of a grid constrained by the position of existing drainage runs in a section of boundary wall that the client had not wanted disturbed, and window sample boreholes, of which there were 4. The trial pit logs were attached as Appendix B to the report. Gerald read each one. They described, in the particular telegraphic vocabulary of geotechnical reporting, the sequence of materials encountered from surface level downward. TP1, for instance, read as follows: 0.00 to 0.30 m, made ground, comprising concrete hardstanding and crushed stone, 0.30 to 1.20 m, loose brown sand with occasional gravel, 1.20 to 2.40 m, medium dense yellowish-brown fine to medium sand with occasional subangular gravel, 2.40 to 2.80 m, dense sand and gravel with chalk fragments, 2.80 m plus, chalk, terminated at 3.0 m. The other trial pits told a broadly similar story with minor variations. TP3 had encountered a layer of soft reddish-brown silty clay between 0.60 m and 0.95 m depth, which was the sort of thing that caused mild concern in structural engineers and mild satisfaction in geotechnical engineers, who enjoyed finding things that caused mild concern in structural engineers. The report noted that this layer was likely localized. The adjacent pits had not encountered it, and recommended that if it was encountered during the slab formation, it should be removed and replaced with compacted granular fill. Gerald noted this recommendation and wrote it in his notebook with a small star beside it, which was his notation for inform the contractor about this specifically and in writing before they start digging. The subgrade modulus of 30 millinewtons per cubic meter was a reasonable value for the material described and was consistent with the plate bearing test results reported in Appendix D. Gerald had, over the years, developed a mild but genuine interest in plate bearing tests. They were one of the more direct and physically intuitive geotechnical tests, in that they involved placing a plate on the ground and pushing it downward until something happened, which was a methodology that appealed to him. The subbase specification. The subbase for a ground-bearing slab was not, strictly speaking, part of the structural reinforcement design. It was, however, enormously important to the structural performance of the slab, and Gerald had spent enough of his career watching otherwise competent designs underperform because someone had skimped on the subbase to take it seriously. For this slab, he specified 150 millimeters of Type 1 granular subbase material, compacted to 95% of its maximum dry density as determined by the vibrating hammer test in accordance with BS 1377. This was, in most respects, a standard specification. The minimum CBR of the subbase material after compaction was to be 30%, which the Type 1 material would comfortably achieve if properly compacted. He wrote the subbase specification into his design report. He then went back and added a sentence specifying that compaction was to be carried out in layers not exceeding 150 millimeters depth, because he had once watched a contractor attempt to compact 400 millimeters of Type 1 subbase material in a single pass with a pedestrian vibrating roller, and the resulting subbase had been, to put it charitably, not uniform. He also specified a 1,000-gauge polythene slip membrane to be laid on top of the subbase before the reinforcement and concrete were placed. The slip membrane served two functions. It reduced friction between the slab and the subbase, which was relevant to the development of crack control reinforcement, and it acted as a vapor barrier, which the client specification had required in the event that the unit was used for any purpose involving moisture-sensitive materials or equipment. Gerald was not certain that light manufacturing necessarily implied moisture-sensitive equipment, but the specification had asked for it and it caused no engineering harm, so he included it. Chapter 3. The Design Calculations. Gerald liked calculations. This was not something he often said aloud, because it sounded peculiar, but it was true. There was something satisfying about the process of taking a physical problem, a slab of concrete, a load, a set of ground conditions, and translating it into numbers that could be combined, compared, and resolved into a specification. The numbers did not argue. They did not change their minds. They did not CC 6 people on emails. They simply were what they were. The design of a ground-bearing slab was, in principle, a relatively straightforward structural problem. The slab was supported continuously by the ground beneath it, rather than at discrete points as would be the case for a suspended slab. This continuous support changed the behavior of the slab significantly. It meant that the slab could not develop large bending moments in the way that a suspended slab might, because any tendency to deflect was resisted by the ground immediately below the deflecting zone. For the Haverstock slab, Gerald used the design approach set out in the Concrete Society Technical Report 34, the industry standard reference for the design of concrete floors, supplemented by his own judgment in areas where TR 34 offered options rather than prescriptions. Loading. The first step was to establish the design loads. The imposed load had been confirmed at 10 knots per square meter. To this, Gerald added the self-weight of the 200 millimeters concrete slab, which at a unit weight of 25 knots per cubic meter gave a dead load of 5 knots per square meter. The total characteristic load was therefore 15 knots per square meter. For the ultimate limit state check, the loads were factored in accordance with the UK National Annex to Eurocode 0. The permanent load was factored by 1.35, giving 6.75 knots per square meter. The variable imposed load was factored by 1.5, giving 15 knots per square meter. The total design ultimate load was therefore 21.75 knots per square meter. Gerald wrote these numbers in his calculation pad. A3, landscape, ruled, purchased from a specialist engineering stationery supplier because ordinary A4 paper was too small for the layout of structural calculations, which required wide columns for values and margins for notes. He had used this brand of calculation pad since university. He did not know whether the supplier was still in business, but as long as they continued to supply them, he did not intend to investigate. He then spent a few minutes checking that 1.35 times 5 was indeed 6.75. It was, and that 1.5 times 10 was indeed 15. It was. This checking of elementary arithmetic was, to a non-engineer, possibly puzzling behavior. To Gerald, it was simply the sensible practice of not allowing errors to propagate through a calculation because he had assumed that a multiplication he could do in his head was correct. He had made errors in mental arithmetic before. He would, he assumed, make them again. The check was the safeguard. Thickness and bending. For a ground-bearing slab with an imposed load of 10 knots per square meter, a thickness of 200 millimeters was broadly consistent with the guidance in TR 34 for medium-duty industrial floors. Gerald confirmed this by working through the simplified design procedure in Section 5 of TR 34, using the subgrade modulus of 30 millinewtons per cubic meter to establish the radius of relative stiffness of the slab. The radius of relative stiffness, L, was given by the equation L equals A cubed O 12, 1 squared, K, caret 0.25, where E was the elastic modulus of concrete, taken as 31 GPa for C32 of 40 concrete at 28 days. H was the slab thickness, 0.2 m. Nu was Poisson's ratio for concrete, 0.2. And K was the subgrade modulus, 30,000 knots per cubic meter, noting the unit conversion from mn to m cubed. Working through this equation, Gerald obtained a radius of relative stiffness of approximately 0.63 m. He then calculated the maximum positive bending moment in the slab under the uniformly distributed load, using the formula derived from Westergaard's solution for plates on elastic foundations. The maximum positive bending moment, occurring at the center of the slab for the loading configuration considered, was approximately 22.5 kNm. He checked this figure. He checked it again. He then consulted TR 34 Table 4.1 to verify that his methodology was consistent with the tabulated approach for similar parameters, and was satisfied that the results were concordant within acceptable limits. Having established the design moment, he proceeded to the reinforcement design in accordance with Eurocode 2, Section 6.1. The required area of reinforcement in the bottom of the slab, calculated using the usual rectangular stress block approach with FCK equals 32 NUMM squared and FYK equals 500 NUMM squared, was approximately 285 mm squared UM in each direction. This was a modest requirement and could be satisfied by a range of bar sizes and spacings. Crack control. Crack control was, in Gerald's view, often the governing consideration in the design of ground-bearing slabs, particularly for industrial floors where the appearance and watertightness of the slab surface was important. Clients tended to regard a concrete floor that cracked as a defective concrete floor, regardless of whether the cracks were structurally significant. And this expectation, while not always technically justified, was one that the structural engineer ignored at his professional peril. The design approach for crack control in ground-bearing slabs followed Section 7.3 of Eurocode 2. The key parameter was the maximum crack width, WK, which was to be limited to 0.3 mm for the exposure conditions applicable to this slab, classified as XC1, the interior of a building with low humidity. The critical area for cracking in a restrained ground-bearing slab was typically the top surface, where restraint-induced tension developed as the concrete cooled and shrunk following casting. The minimum reinforcement required to control this cracking was given by as minute equals Kc times K times FCT, F times act OS, where the various terms describe the geometry and material properties of the section, and where Gerald had been inserting numbers from his material specifications with the comfortable automaticity of someone who had performed this calculation perhaps 300 times over the course of a career. The result, in this case, was a minimum reinforcement area of approximately 360 mm squared OM in each direction at the top of the slab. This was greater than the requirement from the bending check, and therefore governed. Gerald noted this in his calculations with a brief comment. Crack control governs reinforcement area, top and bottom both faces. He underlined crack control governs with a single line, which was his notation for this is the result that determines the design. Chapter 4. The bar schedule. The bar schedule was, in many ways, the climax of the design process. It was a document that translated the abstract numbers of the structural calculations into concrete specifications, not concrete as in the material, though that was involved, but concrete as in specific, actionable, measurable instructions. This many bars, of this diameter, at this spacing, cut to this length, bent in this way. Gerald used a spreadsheet template for bar schedules, a template he had built himself over several years and refined through use. It conformed to BS 8666:2020, which specified the requirements for the scheduling, dimensioning, bending, and cutting of steel reinforcement for concrete. The spreadsheet automatically calculated cut length from the bending dimensions entered, applied the appropriate mandrel sizes for the bar diameter, and formatted the output in a way that was consistent with standard practice and legible to a steel fixer working from a printed copy in conditions that might include wind, rain, and varying degrees of illumination. For the Haverstock slab, the reinforcement layout Gerald settled on was as follows. Bottom reinforcement, both directions, T12 bars at 200 mm centers, giving a provided area of 565 mm squared OM, which exceeded the required 360 mm squared OM. The choice of T12 at 200 centers over, say, T10 at 175 centers, which would have given 449 mm squared OM, sufficient but with less margin, was partly a matter of construction practicality. 200 mm was an easy spacing to mark out and maintain, and T12 bars were stiff enough to hold their position reasonably well during concrete placement, and partly a matter of personal preference, in that Gerald preferred round spacings when they were achievable without significant material cost. Top reinforcement, both directions, the same T12 at 200 mm centers, for consistency of the fabric and simplicity of ordering. The bar schedule would specify top bars in both the NS and EW directions, and the note would indicate that the top and bottom layers were to be identical, which simplified the placing crew's task. Edge reinforcement. Additional T16 bars at the perimeter of the slab, serving as edge thickening reinforcement where the slab transitioned from the main body to the edge detail. The slab edges were to be detailed with a 50 mm chamfer, which was aesthetically tidier than a right-angle edge and reduced the risk of spalling. Movement joints. Gerald specified contraction joints at 6 m centers in both directions, saw cut into the hardened concrete to a depth of 1/3 of the slab thickness, approximately 66 mm, within 24 hours of casting, or alternatively formed using joint formers placed before casting. The choice between saw cutting and formed joints was left to the contractor, who would be better placed than Gerald to judge which method was more practical given their equipment and program. Isolation joints were specified at the perimeter of the slab and around any column bases, where the slab was to be isolated from adjacent elements using a compressible filler strip to prevent differential movement causing distress. Preparing the schedule. Gerald spent most of a Tuesday afternoon populating the bar schedule spreadsheet. He entered each bar mark in sequence, starting with the main bottom mats and working through the top mats, the edge bars, and the miscellaneous items such as the isolation joint filler stops and the spaces. Spaces were, in Gerald's experience, a detail that was easy to specify and easy to ignore, and ignoring them had consequences. The cover to the bottom reinforcement was specified as 35 mm, in accordance with Eurocode 2 requirements for C32040 concrete in XE1 exposure. This meant that the bottom bars were to be supported on proprietary plastic spaces that held them precisely 35 mm above the slip membrane surface. Anything less than this cover risked the reinforcement being too close to the concrete surface, which could allow moisture ingress and corrosion over time. Anything more was wasteful, as the structural effectiveness of the reinforcement decreased as it moved toward the neutral axis of the section. He specified 75 mm square plastic spaces at 800 mm centers in each direction for the bottom reinforcement. This was, he knew, a detail that would be subject to interpretation on site, Because spaces were small, installation was tedious, and some steel fixers regarded them with a particular skepticism reserved for things that seemed unnecessary until the moment they turned out to be necessary. He added a note to his specification: spaces to be maintained in position during concrete placement. Removal or displacement of spaces is not acceptable. He was not certain this note would prevent spacer displacement, but it transferred responsibility clearly enough. He printed the completed bar schedule, checked it once, corrected 2 transcription errors, a bar length that he had typed as 6,150 millimeters when it should have been 6,510 millimeters, and a shape code that he had entered as 21 rather than 12, both of which were the sort of errors that occurred when one was working from handwritten dimensions and one's handwriting was, as Margaret had observed on several occasions, not one's strongest professional attribute. Checked it again, and filed it in the project folder. Chapter 5. The Specification. The structural specification was the document that told the contractor not just what to build, but how to build it. Or more precisely, it told the contractor the technical requirements that the built product must meet, leaving the means of achieving those requirements to the contractor's own expertise and program. Gerald drafted the specification on the Wednesday and Thursday of his 4th week on the project. He worked from his firm's standard specification template, which had been developed over many years and reviewed periodically. The most recent review had been 18 months ago, when Sandra had convened a specification review meeting that had lasted 2.5 hours and resulted in 14 amendments, 3 of which were substantive and 11 of which were typographic. The concrete specification was straightforward. The slab was to be constructed using C32/40 concrete, with a target slump or flow class appropriate to pump-place concrete. Gerald specified S3 slump class, 100 to 150 millimeters, on the assumption that the contractor would use a pump, as was standard practice for a pour of this size. The cement type was to be Gem 2ULL 42.5N or Gem I 42.5N, which gave the contractor flexibility on cement type while ensuring adequate strength development. The maximum aggregate size was 20 millimeters, which was appropriate for a 200 mm slab with T12 reinforcement at 200 mm centers, since the aggregate needed to be able to pass through the reinforcement cage without bridging. The water-cement ratio was to be not greater than 0.55 for the specified exposure class and concrete grade. Gerald included this requirement explicitly, even though it was implied by the concrete grade and exposure specification, because concrete producers occasionally queried whether such limits applied to the particular combination of materials they were using, and having an explicit contractual requirement simplified the resolution of such queries. Concrete placing. The section on concrete placing was particularly important for a ground-bearing slab because the quality of the finished surface was directly related to the skill and care with which the concrete was placed and compacted. Gerald had seen excellent concrete specifications produce poor floors, and he had seen modest concrete specifications produce adequate floors, and the difference was almost always in the execution. He specified that concrete was to be placed in a continuous operation to avoid cold joints, a cold joint being a plane of weakness formed when fresh concrete is placed against concrete that has already begun to harden. For a pour of this size, approximately 42 m by 31 m at 200 mm thick, the total volume was approximately 260 cubic meters, which represented perhaps 20 ready-mix lorry loads. At a typical delivery rate of 1 lorry per 20 minutes, the pour would take approximately 6 to 7 hours, which was achievable in a single shift. He specified that the concrete was to be placed using a long-handled screed or vibrating beam to achieve an accurate surface level, finished with a power float and power trowel to produce a flatness classification of FM2 in accordance with TR34. This being a moderate flatness requirement appropriate for general industrial use, as distinct from the higher FM1 classification required for very narrow aisle, VNA, forklift trucks, which would have required more careful planning and more exacting. Surface finishing. The curing specification required the slab surface to be covered with polythene sheeting immediately after the final troweling, to prevent moisture loss during the critical early curing period. Alternatively, a curing compound conforming to ASTM C309 could be applied, at the contractor's preference. Curing was to be maintained for a minimum of 7 days. Gerald considered whether to specify 10 days, which would have been slightly more conservative, but concluded that 7 was the established industry minimum for the concrete grade and ambient conditions anticipated, and that specifying more than the minimum without a specific technical reason for doing so was not sound engineering practice. Steel fixing. The specification for steel fixing was, in some ways, the most operationally critical section, because errors in the placing of reinforcement were difficult to detect and impossible to correct once the concrete was poured. Gerald had, on one occasion early in his career, been part of a project where the top reinforcement of a suspended slab had been placed at the bottom of the section, an error of such magnitude that it should have been impossible, and yet had occurred due to a combination of unclear drawing details and insufficient supervision. The slab had subsequently required demolition and reconstruction. It had been an expensive and instructive experience. He specified that steel fixing was to be supervised by a competent site engineer, who was to carry out inspections before and after the placing of each layer of reinforcement, and to confirm in writing that the reinforcement was correctly placed, the cover was within tolerance, and the spaces were in position before any concrete was placed. The tolerance on bar spacing was specified as plus or minus 15 mm from the design spacing, which was consistent with BS 8500 requirements. The tolerance on cover was plus 10 mm, minus 0 mm, meaning that less than the specified cover was never acceptable, but some excess cover was permissible. Gerald reflected briefly that it would have been more intellectually satisfying to specify zero tolerance in all directions, but that this would have been practically unachievable and therefore served no useful purpose. Bar laps were to conform to the calculated lap length provided on the drawings. 4T12 bars in C32 of 40 concrete. The basic required anchorage length was approximately 40 times the bar diameter, or 480 mm. Gerald specified a minimum lap length of 500 mm for simplicity, which provided a small margin above the theoretical requirement and avoided the need for steel fixes to measure to the nearest millimeter. Chapter 6. The Pre-Pour Meeting. The pre-pour meeting was held 3 weeks before the planned pour date, on a Wednesday morning at 10 o'clock, in a temporary site office that smelled of plywood and the distinctive slightly sweet mustiness that temporary site offices always seem to acquire regardless of their age, location, or the nature of the works being carried out nearby. Present were Roy Calder, site manager for Benfield Civil Engineering, who arrived first and was seated with a flask of tea when Gerald came in. Derek Faulkner, Gerald's colleague who had reviewed the bar schedule and who had agreed to attend the meeting as a second pair of technical eyes, Philip Moss from Haverstock Properties, who arrived 7 minutes late and had brought a colleague whose purpose was not immediately apparent, and a representative from the concrete supplier, a ready-mix company called Westbury Concrete Limited, named Simon, who had driven from their plant near Devizes and who had a ring binder containing a concrete mix design data sheet that he placed on the table in front of him with the air of someone who expected it to be consulted. Roy Calder opened the meeting in the manner of a man who had opened many such meetings and who regarded the opening of meetings as a task to be accomplished rather than savored. "Right," he said. "We've read the drawings. We've got a few questions. Let's go through them." Gerald produced his copy of the drawings, his calculation package, and his notebook, and arranged them on the table in a manner that he hoped suggested thoroughness without ostentation. Roy's first question was about the joint layout. The drawings showed contraction joints at 6-meter centers, which Roy confirmed he understood, but he asked whether the final base sizes at the perimeter of the slab, which, given the overall slab dimensions of 42 m by 31 m, would not divide evenly by 6 m, could be adjusted. 42 meters divided by 6 gave 7 even bays, which was convenient. 31 meters divided by 6 gave 5 bays of 6 meters and 1 bay of 1 meter, which was inconvenient. Gerald acknowledged that this was a reasonable practical concern. He explained that the joint spacing was a maximum rather than a fixed requirement, and that the contractor could adjust the joint layout within the slab to avoid bays smaller than 3 meters, provided the maximum joint spacing of 6 meters was not exceeded. He suggested that the 31-meter dimension be divided into 5 bays of 6.2 meters, which was within the allowable maximum and produced a uniform layout. Roy nodded and made a note. The concrete mix. Simon from Westbury Concrete presented the concrete mix design. It was C32 by 40, Gem 2 OLL 42.5N cement, 20 mm aggregate, water-cement ratio of 0.50, less than the 0.55 maximum, which was satisfactory, S3 slump class, with a retarder admixture to extend the workability period, which was sensible given the poor volume. Gerald reviewed the mixed design data sheet. He asked Simon about the cement content, 360 kilograms per cubic meter, which was appropriate, and about the aggregate source, which was a quarry in Somerset whose gravel Gerald had encountered on previous projects. He had no objection to the mixed design. He noted that the slump class was S3 and asked Simon to confirm that the lorries would not add water at the point of delivery to increase workability, which was a practice that happened, that contractors sometimes tacitly permitted because it made placing easier, and that was prohibited by the specification. Simon confirmed that drivers were instructed not to add water to loads. Roy confirmed that site management would enforce this requirement. Gerald thanked them both and wrote in his notebook, "Water addition at discharge, not permitted, confirmed by Westbury and Benfield." The meeting continued through the placing sequence, the curing procedure, the sampling and testing requirements, and the expected weather forecast for the poor date, which was, according to Philip Moss, who had checked his phone, probably cloudy with a small chance of showers. Gerald noted that concrete could be placed in light rain, provided the rain did not dilute the surface before finishing, but that in the event of heavy rain, the pour should be postponed. Roy said that he had worked in rain before. Gerald said that he had no doubt about that, and that the specification was clear in any case. The meeting ended at 12:17. Gerald drove back to the office, typed up the minutes, and sent them to all attendees by 5 o'clock. Chapter 7. The Pour. The pour took place on a Thursday in October. It was overcast, as forecast, with a light southwesterly wind and an air temperature of 11 degrees Celsius. These were not ideal conditions. Gerald would have preferred 13 degrees and full cloud cover, which would have reduced the risk of plastic shrinkage cracking by moderating the evaporation rate from the fresh concrete surface, but they were acceptable conditions, and Gerald had poured slabs in Weiss. He arrived on site at 7:15. Which was 4 to 5 minutes before the first concrete delivery was scheduled. Roy Calder was already there, as was the site engineer, a young man named Jack who was in his second year with Benfield and who had the slightly wary attentiveness of someone who knew the day was going to be long and consequential. Gerald's first action on arriving was to inspect the reinforcement. He walked the slab area systematically, checking the bottom mat first, the T12 bars at 200 centers in both directions, the spaces, the edge bars. The bottom mat was laid and appeared correct. He measured the bar spacing at 6 random locations with a tape measure. The spacings ranged from 195 mm to 207 mm, all within the specified tolerance of plus or minus 15 mm. He checked the cover at the corners of several spacer positions by pushing a cover meter probe against the bar and reading the display. The cover was consistently 35 mm to 38 mm, which was satisfactory. The top mat had been placed on stools, proprietary wire stools supporting the top reinforcement at the correct height to achieve 35 mm cover from the top surface. Gerald checked the top mat similarly. One area near the northeast corner of the slab showed a bar spacing of 215 mm, slightly outside tolerance. He pointed this out to Jack, who promptly had it corrected. Gerald noted the correction in his inspection record. At 8 o'clock, he signed the pre-pour inspection certificate, confirming that the reinforcement was satisfactory to proceed with concreting. Roy countersigned it. Jack filed it. The arrival of the concrete. The first concrete lorry arrived at 8 o'clock exactly. This was gratifying. Gerald had attended pours where the first lorry had arrived an hour late, necessitating phone calls, explanations, and the particular mild anxiety of watching a carefully planned pour program begin to unravel before the first cubic meter had left the drum. The lorry reversed carefully onto the site hard standing, guided by a banksman. It was a Schwing concrete pump, an 8 cubic meter drum mounted on a 4-axle lorry, with a mixing drum turning as it moved and with the characteristic slow roar of a diesel engine working at the upper end of its comfortable range. The driver descended from the cab, produced a delivery ticket, and handed it to Jack, who inspected it carefully. The delivery ticket confirmed, Mix C3240, Gem 2 UALL, 8 cubic meters, Water-cement ratio 0.50. Admixture included. Target slump S3. Jack checked each field against the specification requirements. Everything was in order. He signed the delivery ticket, retained the copy, and gave the original back to the driver. The pump, a separate static pump that had been positioned at the south end of the slab, was started. The hose was laid out across the slab. The driver of the lorry positioned his vehicle next to the pump hopper and began to discharge the concrete. The concrete flowed down the chute and into the hopper with the particular sound that fresh concrete makes, a heavy, wet, slightly granular sound, somewhere between water and gravel, that Gerald found difficult to describe but immediately recognizable. It was a satisfying sound. It meant things were proceeding. Slump testing was carried out on the first lorry. Jack took a sample from the midpoint of the discharge, filled the slump cone in 3 layers with tamping, inverted and lifted the cone, and measured the slump. The result was 125 millimeters, which was within the S3 range of 100 to 150 millimeters. Placing, compacting, finishing. The concrete was pumped from the south end of the slab and placed in bays defined by the temporary steel formwork that Benfield had set up to control the pour sequence. The first bay, approximately 6M by 6M, was placed, vibrated using poker vibrators, and struck off level using the vibrating beam screed. Gerald watched the placing with the focused attention of someone who had seen plenty of slabs placed and who knew that most of the things that could go wrong with a concrete slab went wrong during placing. He watched the poker vibrators being inserted at regular intervals. The operators seemed competent, withdrawing the vibrators slowly and reinserting at approximately 500 mm centers, which was consistent with the effective radius of a 65 mm diameter poker. He watched the concrete surface being struck off and verified that the screed rails were at the correct level by comparing the finished surface to the level pegs that had been set out before the pour. The second lorry arrived at 8:22. The third at 8:41. The rhythm of the pour established itself. A lorry would arrive, discharge, depart. Another would arrive. The pump would run continuously. The placing crew would move the hose along the slab. The finishing crew would follow behind. At 9:30, Derek Faulkner arrived on site. He had not been required to attend the pour, but had offered to come along for the first part of the morning, and Gerald was glad of the company if nothing else. Derek watched the placing for 15 minutes, said "looks fine to me," and went to find a cup of tea. The pour continued. Gerald walked the perimeter of the slab, checked the edge formwork, confirmed that the joint formers, where the contractor had opted to use formed joints rather than saw-cut them, which was a valid choice, was still in position and vertical. One former had been displaced slightly by the vibration, and he pointed this out to the site engineer, who had it repositioned. At 12:15, Roy Calder produced sandwiches, cheese and pickle, wrapped in cling film, in a ratio of approximately 1 sandwich per 2 people present, which was adequate but not lavish. Gerald ate his standing at the edge of the slab, watching the placing crew work their way through the 6th bay. By 2:45, the last concrete had been placed. The total volume poured was 263 cubic meters, which was within 1 cubic meter of Gerald's estimate of 262.4 cubic meters, the slight excess being attributable to variations in the sub-base level and minor adjustments to the slab thickness at the perimeter. This level of agreement between estimate and actuality was, in Gerald's experience, slightly better than average. The surface finishing began once the concrete in each bay had achieved sufficient stiffness to take the power float without being disturbed. This typically occurred 2 to 4 hours after placing, depending on the ambient temperature and the rate of evaporation from the surface. On this day, with the 11-degree air temperature and the southwesterly breeze, the concrete in the first bays was ready for power floating by approximately 12 o'clock, meaning the finishing crew were able to work their way across the slab as the later bays stiffened. Gerald left site at 5:30, when the final section of slab had been power troweled and the polythene curing sheet was being rolled out across the finished surface. The slab looked, he thought, acceptable. It was level. It was uniform. It was concrete. Within 28 days, it would be C3240 concrete. Within several decades, if properly maintained, it would still be a concrete flaw. These were modest ambitions, but they were the right ambitions for a ground-bearing industrial slab, and Gerald felt something that was not quite pride but was adjacent to it. Chapter 8. Curing in Early Age. The curing period for the Haverstock slab was, as specified, 7 days. During this time, the polythene sheeting was to be maintained over the surface to prevent moisture loss, and the concrete was to be protected from frost. Though with October temperatures unlikely to drop below 5 degrees, frost was not a significant concern on this project. Gerald visited site on the Monday after the pour, 4 days after the concrete had been placed. The polythene sheets were in position, secured at the edges with timber battens. He lifted a corner of one sheet and pressed his thumb into the concrete surface. It was hard, not fully cured. Concrete takes 28 days to reach its nominal design strength, but hard enough that thumb pressure left no indentation. The slab was behaving correctly. He walked across the slab and inspected the joint lines. The joint formers had been removed on the Saturday after the pour, as planned, and the joints were visible as clean lines across the surface, approximately 3 millimeters wide and of consistent depth. They looked correct. He inspected the slab surface for cracks. This was the inspection he always conducted with the most care, because cracks in fresh concrete were common, and the question was never whether they existed but what they indicated and whether they required action. There were no structural cracks visible. There was a slight pattern of fine surface crazing, a network of very fine cracks no wider than a human hair, affecting only the top few millimeters of the slab surface, in one section near the east wall. This was plastic shrinkage cracking, caused by excessive evaporation from the fresh concrete surface before the surface had gained sufficient strength to resist the resulting tensile stress. The cracks were superficial and structurally insignificant, but Gerald noted them in his inspection record with an assessment of their probable cause. The combination of the light wind and the position of this section of slab relative to the pump hose layout, which may have resulted in a slightly longer exposure time before curing was applied, and a recommendation that no remedial action was required at this stage, but that the section be monitored and assessed again once the curing period was complete. This recommendation was duly noted by Jack in the site records. The compressive strength cubes. As part of the quality control requirements, concrete cubes had been taken from the pour for compressive strength testing. Jack had made a total of 16 cubes, 4 sets of 4, taken from different lorries at different stages of the pour, which had been stored in a water tank on site for curing in accordance with B.Eng 12,390-2. The procedure for taking cubes was prescribed in B.Eng 12,350-1. The fresh concrete was sampled at the point of discharge, placed in 150 mm steel cube molds in 2 layers with compaction by tamping rod. The surface was struck off level, and the molds were covered with polythene and left to cure for 24 hours before demolding. The cubes were then immersed in water at 20 degrees Celsius until the required testing age. 4 cubes from the first set were tested at 7 days. The results were 28.4, 29.1, 27.8, and 30.2 NUMM squared. The mean was 28.875 NUMM squared, which was within the expected range for C32 of 40 concrete at 7 days, the characteristic strength at 7 days being typically approximately 65% of the 28-day strength, implying an expected 28-day strength of approximately 44 NUMM squared, comfortably above the characteristic minimum of 40 NUMM squared. The 28-day cubes were tested 4 weeks after the pour. The results from the 4 sets were as follows. Set 1, 42.3, 43.7, 41.9, 44.1 NUMM squared. Set 2, 43.2, 42.8, 44.0, 43.5 NUMM squared. Set 3, 41.7, 42.9, 43.1, 42.2 NUMM squared. Set 4, 44.6, 43.8, 42.7, 44.9 NUMM squared. The overall mean was approximately 43.3 NUMM squared, and the minimum individual result was 41.7 NUMM squared. Both values exceeded the C32 of 40 characteristic strength of 40 NUMM squared, and the compliance assessment in accordance with B.Eng 206:2013 plus A2:2021 confirmed that the concrete conformed to the specified strength class. Gerald recorded the results in the project file, completed the compliance assessment form, and wrote a brief note to Philip Moss confirming that the concrete strength had been confirmed satisfactory. Philip Moss acknowledged the email promptly, CCing 5 people. Chapter 9. Joint Sealing and Surface Treatment. The contraction joints in the slab surface required sealing to prevent the ingress of water, grit, and debris. This was not a structural requirement in the strict sense. The joints were there to allow the slab to crack in a controlled manner at planned locations, and the crack control reinforcement ensured that cracks remained tightly closed, but it was a practical requirement for a warehouse floor, where contaminants entering unsealed joints could, over time, cause spoiling of the joint areas and deterioration of the joint itself. Gerald specified a semi-rigid polyurethane joint sealant, applied to the cleaned and primed joint to a minimum depth of 25 mm and a width matching the joint width. The semi-rigid formulation was preferred over a flexible sealant for an industrial floor because it provided support to the joint areas under trafficking, reducing the risk of areas chipping. This distinction was one of those details that mattered in practice but rarely featured in general specifications, and Gerald had added it to his standard specification following an early career experience with a client who had specified flexible sealant and subsequently complained about damaged joint edges. The joints were to be sealed not less than 4 weeks after the pour, to allow the concrete to complete the majority of its drying shrinkage before the sealant was applied. Applying sealant too early meant that subsequent concrete movement could overstress the sealant and cause premature failure. The surface treatment specified was a penetrating silane or siloxane sealer applied to the dry and clean concrete surface in accordance with the manufacturer's instructions. This sealer provided a degree of water and oil resistance without altering the surface appearance significantly, which was preferred by the client over a surface coating that would have required periodic maintenance. Benfield duly applied the joint sealant and sealer in the 6th week after the pour. Gerald visited site to inspect the joint sealing. The joints were cleanly sealed. The sealant was well adhered and showed no voids or pinholes, and the sealer had been applied uniformly. He recorded his satisfaction with the work in his inspection report. Chapter 10. The Completion Report. The completion report was Gerald's final act of involvement with the Haverstock slab. It was a document of approximately 14 pages, summarizing the design basis, the material specifications, the as-built deviations, of which there were none significant, the test results, and the recommendations for ongoing maintenance of the floor. He drafted the report over 2 days. The writing of it was, in its own way, the most reflective part of the project, the point at which he assembled all of the threads of the work and wove them into a coherent account. He was aware, as he wrote, that the report was unlikely to be read in full by anyone other than himself and, possibly, whoever eventually prepared a health and safety file for the project. This was the fate of most completion reports, and he was at peace with it. The maintenance recommendations section specified that the slab surface should be inspected annually, that joint sealant should be replaced when it showed signs of debonding or failure, that the floor surface should be kept clean of abrasive materials that could damage the surface latents, and that any cracking observed during the life of the floor should be assessed by a structural engineer before any loading changes were made. He added a note on maximum imposed loads. The slab had been designed for 10 knots per square meter uniformly distributed, and point load from racking systems or machinery were to be assessed separately. This note would, he hoped, prevent anyone from placing a particularly heavy piece of equipment on the floor in the future without stopping to consider whether the floor could accommodate it, though he harbored no illusions about the certainty of this outcome. Handover. The formal handover of the completed slab occurred on a Friday morning. Gerald attended on behalf of Perimeter Structural Consultants. Roy Calder attended on behalf of Benfield Civil Engineering. Philip Moss attended on behalf of Haverstock Properties, and he had brought 2 colleagues, one of whom turned out to be the future tenant of the unit, a man named David Hewitt who operated the light manufacturing facility that had been the basis of the loading assumption at the outset of the project. They walked across the slab together. David Hewitt asked a few questions about the floor's load capacity, which Gerald answered clearly and without excessive technicality. Philip Moss asked whether the surface crazing noted in the east section was a problem, and Gerald explained that it was not structurally significant, that it was a cosmetic issue affecting only the surface, and that it was unlikely to worsen in service. Philip Moss nodded and made a note. Roy Calder asked no questions. He had been present for the entire pour, the entire finishing operation, and the subsequent inspections. He already knew the answers. The handover certificate was signed. Photographs were taken of the completed slab. Copies of the completion report, the bar schedule, the concrete test results, and the design calculations were placed in an envelope and handed to Philip Moss. Philip Moss handed the envelope to one of his colleagues. Gerald drove back to the office. On the way, he stopped at a filling station and bought a cup of coffee. He drank it in the car park. It was adequate, though the water-to-coffee ratio was not precise. He finished it, drove the remaining 12 miles to the office, and arrived at 1:45, which was 15 minutes before his afternoon appointments. He updated the project file to indicate that the completion report had been issued and the handover had taken place. He closed the project folder on his computer. He created a new folder in the archiving system and moved the project files into it. The Haverstock slab was, from Gerald's perspective, complete. Chapter 11, Reflections. Some weeks later, Gerald was at his desk reviewing the pile cap calculations for the Chippenham scheme, which had, in the interval, become more than mildly urgent, when he received an email from Philip Moss. The email said, in its entirety, "Hi Gerald, the tenant has moved into Unit 4B and the floor looks great. Is very happy with it. Thanks for your help on the project." Philip Moss had CC'd 4 people on this email. Gerald read the email twice. He then replied, "Thank you, Philip. Glad to hear it's working well." He proofread the reply, found nothing to change, and sent it. He did not CC anyone. He sat for a moment. The Chippenham pile caps waited in their spreadsheet. The office hummed with the sound of computers and the occasional distant sound of a printer. He thought about the slab, about the subgrade modulus and the radius of relative stiffness, about the T12 bars at 200 centers and the 35 millimeters cover and the plastic spaces that had, as far as anyone could tell, stayed in position throughout the pour, about the slump test result of 125 millimeters and the 28-day cube strength of 43.3 NUMM squared, about Roy Calder's steel toe cap boots and the first concrete lorry arriving at exactly 8 o'clock and the polythene curing sheet being rolled out across the finished surface in the late afternoon of a cloudy October Thursday. The slab existed. It was 200 millimeters thick, reinforced with T12 bars at 200 centers top and bottom in both directions, sitting on 150 millimeters of compacted Type 1 subbase with a 1,000 gauge polythene slip membrane between the subbase and the concrete. It was, by any objective measure, an ordinary ground-bearing industrial slab. It had been designed correctly, specified clearly, constructed competently, and inspected thoroughly. It had achieved its design strength. Its joints were sealed. Its surface was level. It would do its job quietly and without acknowledgement, bearing the loads placed upon it, distributing them to the ground below, absorbing the daily trafficking of forklifts and pallet trucks and the occasional footfall of workers making their way across it, for years or decades, until the building around it was eventually demolished or altered and someone had to think about it again. There was something deeply, profoundly satisfying about this. Gerald could not have explained exactly why to someone who had not also spent a career in structural engineering. But the slab was there. It worked. That was enough. He returned to the pile caps. Epilogue, Slab 4B, 5 years later. 5 years after the completion of the Haverstock slab, Gerald received a call from Philip Moss. Philip Moss had, in the interval, changed jobs twice and gained a somewhat more direct telephone manner. He explained that Haverstock Properties were planning to extend the unit, an additional bay, approximately 8 meters by 31 meters, to be added to the north end of the existing building, and they wanted to know whether the existing slab records were available and whether the extension slab could be designed by the same engineer who had done the original. Gerald confirmed that the records were available. He confirmed that he was available. He pulled the archive project file from a server. Havs 4B. He opened the folder and found, exactly where he had placed them 5 years ago, The design calculations, the Bosch schedule, the specification, the concrete test results, and the completion report. Everything was in order. Everything had been properly documented and archived. He called Philip Moss back and confirmed that the extension design could be commenced the following week, subject to receipt of a project brief and the relevant ground investigation for the extension area. Philip Moss said that was excellent and thanked him. Gerald said not at all and ended the call. He opened a new project folder on his computer and typed its name, Havs 4B Extension. He stayed at this for a moment, then went to make a cup of instant coffee. 1.5 teaspoons. Appendix A, Key Design Parameters. For the benefit of any reader who has, through determination or insomnia, reached this appendix, the following summary of key design parameters is provided as a reference. Slab type, ground-bearing flat slab. Slab thickness, 200 mm, overall plan dimensions, 42.0 m x 31.0 m. Concrete grade, C32-40, in accordance with B.Eng 206:2013 plus A2:2021. Reinforcement grade, B500B, T12 bars. Exposure class, XC1. Design working life, 50 years. Subgrade modulus, 30 millinewtons per cubic meter. Subbase, 150 mm type 1 compacted granular material. Slip membrane, 1000 gauge polythene. Bottom reinforcement, T12 at 200 centers both ways, provided area 565 mm². Top reinforcement, T12 at 200 centers both ways, provided area 565 mm². Nominal cover, 35 mm top and bottom. Contraction joint spacing, 6.0 m maximum, 5x 6.2 m bays in 31 m direction. Isolation joints, at perimeter and column bases. Design imposed load, 10 knots per square meter uniformly distributed. No concentrated point loads. Self-weight, 5 knots per square meter. Total characteristic load, 15 knots per square meter. Design ultimate load, ULS 21.75 knots per square meter. Required reinforcement area, bending 285 mm². Required reinforcement area. Crack control 360 mm². Governing. Crack control. Actual 28-day compressive strength, mean of 16 cubes 43.3 Nmm². Minimum individual result, 41.7 Nmm². Compliance assessment, pass. Appendix B, a note on terminology. Several terms used in this account may require clarification for the general reader. Characteristic strength refers to the compressive strength below which not more than 5% of results from a population of tested specimens would be expected to fall. A concrete grade of C32-40 implies a characteristic cylinder strength of 32 Nmm² and a characteristic cube strength of 40 Nmm². The cube strength is the value measured by the cube test described in Chapter 8. DXA is a unit used in document typesetting, not in structural engineering, and has no relevance to this story. Eurocode 2 is the European standard for the design of concrete structures, adopted in the United Kingdom as BSEN 1992-1-1:2004 plus A1:2014. It provides design rules for reinforced and pre-stressed concrete structures of all types. The rules relevant to this account are principally those in Section 6, Ultimate Limit State Design of Cross-Sections, and Section 7, Serviceability Limit States, including crack control. A ground-bearing slab is a slab that is supported directly by the ground. This is in contrast to a suspended slab, which spans between supports and is not in direct contact with the ground below. The distinction is significant because it changes the structural behavior. A ground-bearing slab has continuous support and therefore develops lower bending moments than an equivalent suspended slab, but is susceptible to differential settlement and heave if the ground conditions are not uniform or if tree roots are present. Latence refers to a weak layer that forms at the surface of fresh concrete due to the upward migration of water, cement, and fine particles during compaction and early curing. It is softer than the underlying concrete and, in floor construction, is typically removed by the power floating and troweling process, or by grinding if it proves resistant. Excessive latence can indicate over-vibration or mix with too high a water content. A poker vibrator is a cylindrical device, typically 25 mm to 75 mm in diameter, containing an eccentrically rotating mass that causes the device to vibrate at high frequency when switched on. Inserted into fresh concrete, it causes the concrete to temporarily liquefy around it, allowing entrapped air to escape and the concrete particles to pack more densely. Proper vibration is essential to the strength and durability of concrete. The effective radius of vibration, the distance from the poker within which the concrete is adequately compacted, is approximately 4 to 6 times the poker diameter. The radius of relative stiffness is a parameter used in the analysis of slabs on elastic foundations. It represents the distance over which the slab distributes a point load to the supporting ground. A slab with a larger radius of relative stiffness distributes loads over a wider area, which reduces bending moments but increases the bearing pressure away from the load application point. The radius of relative stiffness depends on the slab thickness, the elastic modulus of the concrete, and the stiffness of the foundation soil. A slip membrane is a sheet of polythene or similar material placed between a ground-bearing slab and its subbase. Its primary structural function is to reduce friction between the slab and the subbase, which affects the behavior of crack control reinforcement. It also serves as a vapor barrier. The thickness of the polythene is measured in gauge. 1 gauge is approximately 0.25 microns, so 1,000 gauge is approximately 250 microns or 0.25 millimeters. This is thin. It is also adequate. Type 1 subbase is a graded crushed rock material conforming to the specification in the Specification for Highway Works, Series 800. It consists of crushed rock, crushed slag, or crushed concrete with a grading control to ensure adequate compaction characteristics. It is the most commonly specified granular subbase material for floor and pavement construction in the United Kingdom and provides a stable, well-drained foundation when properly compacted. Appendix C. Acknowledgements and selected references. The author wishes to acknowledge the following references, which inform the design approach described in this account. The Concrete Society, Technical Report 34, Concrete Industrial Ground Floors, A Guide to Their Design and Construction, 4th edition. This is the primary industry reference for the design of industrial concrete floors in the United Kingdom. It covers all aspects of design from ground investigation to surface finish specification, and is a document that Gerald consulted at every stage of the design process described in this account. It is not, by general standards, a page-turner. B.Eng 1992-1-1:2004 plus A1:2014, Eurocode 2, Design of Concrete Structures, Part 1-1, General Rules and Rules for Buildings, together with its UK National Annex. The Eurocode for Concrete Structures provides the design rules applied in the calculations described in Chapter 3. B.Eng 206:2013 plus A2:2021, Concrete, Specification, Performance, Production, and Conformity. This is the standard that governs the specification and testing of concrete, including the characteristic strength requirements and the compliance assessment procedure described in Chapter 8. B.S. 8666:2020, Scheduling, Dimensioning, Bending and Cutting of Steel Reinforcement for Concrete, Specification. This is the standard referenced in the preparation of the bar schedule described in Chapter 4. B.S.EN 12390-3:2019, Testing Hardened Concrete, Part 3, Compressive Strength of Test Specimens. This is the standard to which the cube tests described in Chapter 8 were carried out. Westergaard, H.M., 1926, Stresses in Concrete Pavement Computed by Theoretical Analysis. This paper, now approaching its centenary, remains the basis for the theoretical analysis of slabs on elastic foundations. Westergaard solutions, derived for airport and highway pavements, were adopted for industrial floor design and remain in use today with appropriate modifications. Sylvain A. 5 Hardback Notebook. The author considers this an essential piece of equipment and wishes to place on record his hope that it continues to be manufactured. And The Reinforcement of Slab 4B, first published in the author's imagination, shortly after a long site meeting.